example for divide and conquer approach. It's the main topic of this module. Yeah. Binary search. Yeah. But here we also will use the elimination view to understand divide and conquer. You can apply many different views. Okay, yeah. All right. Search an ordered array. This time we require our data is ordered. Okay. If you have this good property, ordered property, you should take advantage of it. Take advantage of it. So that means if you still apply the linear search, then you didn't take advantage of this order information. Yeah. So the binary search should be the choice. Yeah. Because the binary search is so useful in the real world applications, we need to spend some time to learn important properties for the binary search. Okay. All right. Given an ordered array like this, and the search key V. Okay, yeah. How to find an index I such that V equals A of I. Yeah. So if you compare it with our linear search problem, you can see the only difference is here. We have an ordered array here, but that one unordered array. Main difference. All right, so now let's do the analysis. Idea, still that reduce the problem size. Yeah. But here, for the problem size reduction, we compare the given key with the element in the middle. We know the element in the middle we call the median, right? Here, the median. Yeah. We use that median concept. So we compare the V with the median of the current array. Okay. All right. So then, how do we apply elimination method to reduce the problem size? After one comparison, you can reduce the problem size approximately by 1/2. Approximately 1/2. That much reduction. That's pretty good. 1/2 reduction. That's pretty good. Okay. All right. Yeah. So that here, how to take advantage of the ordered data property. Yeah, so let's look at the detail. Yeah. All right. Explore the order property. Yeah. All right. Look at this diagram. Suppose our data is ordered, ascending order, and there is a key. V, there is a key. Yeah. Okay. And to do comparison, to do our first comparison, there are many different ways to do first comparison. You have freedom. Here you have a lot of freedom to choose the first element in the array for the comparison. You have freedom to choose. Okay, yeah. One way you compare V with the last element, A sub n minus 1, or some element inside, interior element in the array. Yeah. Okay. Yeah. Now we want to see which way is the best. We have a lot of freedom. So we need to make this decision, first decision. which element, if we do the comparison, would give us the best overall result. That's the goal, best overall result. Or another way, give us the best result to handle the worst case. Yeah. Here I also like to emphasize. Yeah. We need to, so here, focus on the worst case. Okay? Because when we have a computing problem, we need to find the best solution for the worst case, right? That's in general. We need to find the best solution for the worst case. Here, we have the same situation. We need to find the minimum number of comparisons for the worst case. That's our goal. Okay, yeah. All right, so now let's work here. Implement. In our analysis, we need to keep this goal in our mind for the worst case. All right. Question. After one comparison, how many elements can be eliminated? Okay, all right, so here, if you look at V, comparing it with the last element, then you have two cases, two possibilities. One is the best case. Yeah. V greater than A n minus 1. That's the best case. Because after that comparison, you already know V greater or equal to A n minus 1. You don't need to do further comparisons. Yeah. V greater than the largest element. No further comparison needed. Okay, yeah. That's the best case. All right, yeah, just one comparison. But other than this best case, other cases, V less than A sub n minus 1. So if it's not the best case, then you need to do a lot of work, because you only know V is less than A sub n minus 1. And the relationship of V with other elements, you don't know. You need to do more comparisons, not more. Okay, yeah. So here you can see you have one best case that you need a minimum number of comparisons. One comparison, that's minimum. And another one, you need more comparisons here. So which part you should focus on? Which part you should focus on? Not the best case, right? The other cases, or other worst cases. Other worst cases. Yeah. Here, I like to, yeah. So here I would like to spend a few minutes to, convey some interesting idea to you. Yeah. Because from the homework assignment number 1, I noticed several students, they gave me the solution, not for the worst case. Okay, not the worst case. Yeah, actually better than the worst case. Better than worst case. Yeah. So here I want to convey an idea, because when you consider several possible cases, so you do comparisons. I remember in one of our questions, like sorting 4-element array. Yeah. When you do comparison, for example, compare x2 and x3, so you get two possibilities. One, x2 less than x3, another x2 greater than x3. Okay, but these two cases may not be equivalent. Okay, so I hope you understand it equivalent, because the situation caused by these two cases not symmetric. Okay, symmetric like a mirror, symmetric like a mirror. Okay, yeah. So because when we do comparison, the first comparison, x1 and x2, we have two cases. Oh, sorry, x1 greater than x2. But these two cases symmetric. Okay, yeah, x1 less than x2, x1 greater than 2, just like a mirror. Okay, so symmetric. If you switch x1, x2, you get the same situation. In this way, we only need to consider one of the two cases. We do not need to consider the other symmetric case, equivalent symmetric case. But here, you may not get a symmetric equivalent cases. So you should consider both cases. When you need to consider both cases, just pick the worst one. There is one better than the other. Okay, one better than the other, but you should focus on the worst one. Okay, yeah, that's from the homework question, sorting 4-element array. Yeah, but here we have the similar situation. We have two cases here. These two cases are not symmetric, not equivalent. One is worse than the other. So we should focus on the worst one, not a better case. Okay, yeah. So the view of this one, there is an interesting argument for this kind of approach. Interesting argument. So it's called adversary argument. Yeah. So this way of thinking is very useful. So I like to introduce this adversary argument to you. Okay? We can imagine we fight against some adversary, our adversary. Okay? Yeah. When we make a comparison, we imagine there is an adversary. Okay? Yeah. So here, the story is like this. Yeah. When we do comparison, x2, x3, which one larger, which one smaller? Yeah. There are two possibilities, right? Yeah. But which possibility we should take? We ask our adversary. Our adversary will tell us which one to take. But a smart adversary would always choose the tougher one, right? For you. Because our adversary always wants to make our life harder, not easier, right? So this is the argument, adversary argument. When you do any comparison, you fight against some very smart adversary. The adversary tries to make you work harder. The adversary always pick the worst case to you. You need to work on this harder case. That's the adversary argument. So if you use this adversary argument, then you always work on the worst case. Now here, if we use this argument, the adversary would pick this part. Yep. So we need to work on the case V less than A sub n minus 1. Then, if you look at the problem size reduction, you only reduce the problem size by 1. After one comparison, you reduce the problem size by 1. That progress is too small. One comparison size reduced only by 1. That's too slow. Okay? Can we imagine some other locations? Yeah, another way to see it, very visual, right? When you have something bad could happen, you need to worry. You know, it's very likely You have that. Okay, that's another way you view this. So we should always consider the worst case. Consider the worst case. Yeah. All right. Here, where now we choose the element, we fight against the adversary. How do we take a smart strategy to fight against our adversary? We pick the element right in the middle, or more precisely, we pick the medium element. Okay? We pick the medium element. Then we ask our adversary. So which case you want to give us? The adversary can choose V less than the median, right? Or V greater than the median, right? There are only two choices. Or greater equal, equal we know, we stop, right? Yeah. So here let's consider not equal. Because if equal, we find the element, the solution already there, we can stop. So it's not a worst case, right? Yeah. If equal, it's not a worst case. Okay. We want to all the way go to the end. That's the worst case. Okay. All right. So now we have these two questions.
This Murphy's law, the median, would that be part of the best case, I'm guessing, or is it just it doesn't matter whichever one?
Right, doesn't matter because there is no worst. The two cases are equal. Yeah, yeah. So here for this case, yeah, V less than the median case 1, V greater than the median case 2. These two cases are equally good or equally bad, right? In this way, our adversary cannot make our life harder because two cases are the same. No matter which one the adversary picks. Yeah. Right. Yeah. So when you choose the median, you avoid the bad consequence of the Murphy's law. You have the best strategy to fight against the adversary. Yeah. That's the point. Yeah. Because, yeah. So here, another part of that adversary argument, how to fight against the adversary argument. You try to make a decision that gives you two equally well cases. Then your adversary cannot make it worse, right? Equally well, equally good. So the adversary just pick one of the two equal cases. Okay, for you, that's the best strategy to fight against some tough adversary. Okay, yeah. All right, yeah. So here, by this view, we can work on the, yeah. Also, another view we call a balancing principle. Okay, yeah. When you have a chance to distribute your data, distribute it in a balanced way. That's another view. Okay, yeah. So you can view the same question in different ways to help you understand it better. Yeah, better. All right. Yeah. Next, efficiency analysis of binary search. Now, we want to do some serious analysis work. Yeah. All right. Yeah. So here we want to look at the number of comparisons we need for the worst case. Yeah. So let's do some calculation. Okay. We want to derive precise formula, not approximate formula, precise formula here. Okay. All right. So let's consider the diagram here. So you compare it with the median. Okay. Yeah. Whatever the result you get, you always drop 1/2 of the current data. Yeah, approximately 1/2. So you can argue may not be precisely 1/2, but it's good enough, approximately 1/2. Okay, yeah. All right, after that, the second comparison, you compare it with the current median, the new median, the current median. So you drop another 1/2 of the current file, and so on. Keep doing this until you cannot do this forever, right? Yeah. At some point, only one element left. You just do last comparison. One element left. So you can terminate. Your algorithm can terminate in this way. Yeah. Every time. Yeah. So here, if we do a chart on the problem sizes, you can see after first comparison, the size is n/2. After second comparison, size is n/4. Approximately, not exactly, approximately. After k comparison, the size of the data you need to work is n/2 to the kth power. Okay, yeah. But here we need to estimate for what k we reach the end. That's important. What is the last k? Yeah, our kth comparison. After the kth comparison, we reach the end. We want to know that particular point. How do we figure out? How do we use math formula to describe that last k? Yeah, this step, we need to work carefully. All right. At what time should we stop splitting? Yeah. When the problem size falls in what range we should stop? Think about that question. The problem size. Yeah. Problem size, you just imagine there is a line segment with this length. That's the problem size, line segment with this length. How many elements this little line segment can cover? Think about that view. Okay, yeah. All right. That line segment first, yeah, before I show you the formula, look at that little line segment. First, it should not cover at least 2 elements, right? If that line segment covers 2 elements, you have 1 chance to split it. So the length of that line segment should be strictly smaller than 1. Strictly smaller than 1, then it can cover at the most 1 element, right? Cannot cover more than 1 element. Okay, at the most 1 element, then you do not need to do splitting anymore. Only 1 element falls in the range. That's the last one. Yeah. So based on that observation, the data size, you should stop after last comparison. Your data size becomes strictly less than 1. Then you stop. Okay? Yeah. All right. Then look at this inequality. We want to write the most accurate inequality to describe the range for k, for the last comparison k. Here, after kth comparison, n/2 to the kth, that's the data size, should be strictly less than 1, but it's previous before kth comparison. After k-1 comparison, its previous data size. This is its previous data size. Should be greater or equal to 1. Yeah. Then you can do one more comparison. Greater or equal to 1, you have at least 2 elements. So you know, for the worst case, right? We consider the worst case. So you need to do another split. So this is the inequality that give us the range for K as our last comparison. Last comparison. Okay, all right. Now we need to solve this inequality for K. Yeah, because we need to see the range for K clearly in terms of N. Okay, so let's do simplification. Yeah. After we remove the common denominator, yeah, so you see 2 to the K minus 1 less than or equal to N and strictly less than 2 to the K. That's the new inequality. And in this one, we can see K a little better, but still not the straightforward way, yeah, because still K appears at exponent. So we want to see the range for K directly, not indirectly. Here, still indirectly. So we should take log base 2 to see the range for K directly. Okay, yeah. So let's take log base 2, so we get this inequality. K minus 1 less than or equal to log base 2 of N and strictly less than K. Yeah. Yeah. So now we can see the range for K better. Yeah. So what is the worst case K number? Yeah. Still, we need to do some improvement here. Yeah. You can see this log base 2 of N, this is not an integer expression. Yeah, log base 2 for arbitrary positive integer N, this expression in general, not an integer. Yeah. But our K must be an integer. So for this log base 2, we should use integer expression to describe the K range, integer description. Yeah. That means we should use floor function or ceiling function. 2 cases, floor function or ceiling function. 2 possible cases here. Okay, yeah. Yeah. So let's take a look. So which case we should use? Okay, yeah. All right. Derive the worst case formula. Okay, yeah. So when we start, yeah, here we just rewrite the previous, yeah, this inequality. Look at the previous inequality. This is the one. Now we just do some algebraic manipulation. So we get the range for K. This is range for K. But the only thing that is not very good, log base 2 of N is not an integer expression, We want to make it some integer expression. Okay, yeah. All right. So for this log base 2, should we take ceiling function? Yeah. This log base 2 of N strictly less than K. When we take ceiling function, it's less than or equal to K. Look at that. Less than equal to K. And this side, we should take the floor function, right? Floor function. Yeah. That side greater or equal to K. And we want the integer expression. So the right hand side, we should take floor function. Left hand side, we should take ceiling function. to improve it. Look at that, improve it. Okay, yeah, all right, here. So actually from this one, we can get ceiling function of log base 2 of n less than or equal to k less than or equal to 1 plus okay, yeah. So we can get that. Yeah. We can get that. Yeah. But that one still not good enough. Not good enough. Yeah. Because that one we get a range, right? We get a range for k. Now a better k expression is k equals some expression. This is better than the range, right? The range, you have more than one probabilities, right? More than one probability, but k equals one exact expression, only one probability, only one case. So you want to do better than this range, better than this one, okay? Yeah. So how to do better? Yeah. Let's tighten our inequality. Yeah. We can make it tighter. Yeah. It's not tight enough. So we tighten it, still loose a little bit. So let's make this inequality, closer to the final result. Tighten it, okay? So how to tighten it? How to tighten it? Look at this inequality. And strictly less than 2 to the k. Yeah. Both integers. One integer is strictly than the other. What can you get? Integer n is strictly less than 2 to the k. Can you get a better one like this? Because we want the better one, that's the equal case. Can we get a better one? N plus 1 less than or equal to 2 to the k? That's a better one. N plus 1. Yeah, we increase that number by only 1. It should not be greater than 2 to the k, right? It should be at the most 2 to the k. Because we know 2 to the k strictly greater than n. So we increase n by 1, still not greater than 2 to the k. So less than or equal to 2 to the k. So can you see this inequality is a little better than the previous one? So that's what I mean, tighten it. Okay? Make it tighter, tighten our estimate. Okay? Yeah. All right. Based on this new one, yeah. So here we have this new observation. Now we take log base 2 on this new inequality. We get k greater or equal to log base 2 parenthesis of n plus 1. Okay? Yeah. So this time, if we apply ceiling function, it should be on ceiling function on log base 2 of parenthesis n plus 1. One better than the previous estimate. Previous, we don't have the n plus 1. Okay? Here, we only improve by one better inside the logarithm, inside log base 2 function. Still better, right? That one more still better. Okay, yeah, all right. So now, based on this new estimate, we can get a better k formula conclusion. 2 formulas, yeah. Because when we have this, we have 2 ways to describe k, right? From upper bound and from lower bound. There are 2 different formulas we can write. Yeah. Yeah. So one lower bound. This is the lower bound. Right? Second, this is upper bound. All right. Yeah. Fortunately, both upper bound, lower bound, they are the same. The upper bound expression, lower bound expression, they are the same. We can prove it. Yeah. Here, I just skipped the proof. Yeah, I can prove it. Yeah, but I want to save some time. Yeah. Okay. So these two bounds happen to be the same. So that means our K-max formula, you can use either one. Both correct. Both versions. There are two versions. These two versions have different expressions, but they have exactly the same values. Same values. Okay. All right. Yeah. And this formula, you can find it in the appendix of our textbook. Okay. Appendix of our textbook. In order to prove it, we can use mathematical induction to prove it. Okay. Yeah, but here I skipped that part. Mathematical induction. Yeah. You need to do some work. Yeah. Mathematical induction, you can prove it. A lot of work. Yeah, I just skip it. Okay. Yeah. All right. Then, now the conclusion, the final conclusion. The best case won, right? Binary search, for the best case, when you do the first comparison, V, compare it with the median, they happen to be the same. The best case. V equals the median element. Yeah, that's the best case. Then the worst case. Worst case. One of the above expressions. Okay? Yeah. One of the above expressions. Yeah. Yeah. All right. But the question, average case. How to calculate the average case? Here, a little harder, yeah, but interesting, because here, when you calculate the average case, look at the binary search. Binary search corresponds to a binary tree. Binary tree, the data distributed, it's not even distribution. There are many levels. On top, only one element. Then below the next level, you have more and more elements. Double each level, approximately double. Okay, yeah. Because the bottom level, won't be double. Yeah. Other than that, double. Okay, yeah. All right. The question, can we say, if we just take average of best case, worst case, can we say the worst case, average case equals best case plus worst case divided by 2? No, yeah. Because only when the data distribute evenly, you can say that. Even distribution, okay? All the cases distributed evenly, okay? Even, but here, it's not an even distribution. Different levels, the number of elements distributed in different levels are different. If the number of elements distributed in all levels are the same, then you can use this formula. Yeah, but here, different. Okay, yeah. All right. So we cannot use this way. Okay, yeah. But how to calculate average case? Here, I like to show you one example to calculate the average case. So let you see the detail. The correct way to calculate number of comparisons for the binary search. Okay, yeah. All right. Yeah, the average case efficiency. Here, I like to use a simple example, n equals 7. Yeah. n equals 7 because the binary tree from this example, you get a complete binary tree. You get a complete binary tree. Okay, yeah. So let's take a look. What is the exact answer, not approximate? Some students use approximation formula. Yeah. But many times I ask you for the exact answer, not approximate answer. Here we want to find the exact answer for the average case efficiency. Okay, yeah. All right. So let's do the speed point 3, average case efficiency of binary search. Okay, all right. All right. Yeah. So let's draw that binary tree. Yeah. We have a 7-element sorted array. So let's start with this diagram. Yeah. 7 positions in ascending order. All right. So we compare it with a key. The median, the first one, we compare it with the median. So the median element should be at top of the binary tree. Our first comparison. Yeah. All right. Yeah, here, there is a probability P issue. Yeah. But here, I like to only look at the, V is one of the elements in this array. Yeah. Let's forget about the probability P. Okay. Yeah. Because for P, you have a situation, V is not in the array. Okay. V is not in the array. When I give you a question, I may tell you the V is in the array. We make this assumption. V is in the array. Okay. Then we calculate the average number of comparisons. All right. The first comparison with element at position 4, so we put it at the root of the binary tree. So that's the root element. All right. Then this root element corresponds to 1 comparison. So I put that 1 for this level, for the element in this level. Okay. Then we move to the next level. Next level, left-hand side, we should do comparison with 2, and the right-hand side, we should do comparison with element at position 6. Okay. So these 2 elements correspond to number of comparisons 2. Okay, next level, we need to do 2 comparisons to see, to get V equals element 2 or element 6. Okay, yeah. Then next level, 1, 3 at left-hand side, 5, 7 at the right-hand side. Okay, and this level, we need 3 comparisons. All right, then it's all the cases. When we take average, we should consider all these 7 cases. All right, yeah. We want to accumulate the total number of comparisons for all 7 cases. Accumulate, add them up. All 7 cases. Okay, yeah. Let me write the final formula. Try to understand this final formula. Okay, yeah. Look at the average. Level 1, we only have 1 element and each one comparison. Yeah. Okay, yeah, yeah. So level 2, we have 2 elements and each element we do 2 comparisons. Level 3, we have 4 elements. Number of elements. Okay. Number of comparisons. each. Okay, yeah. 3 times 4. Okay, then we add up all the comparisons for all 7 cases, but for the average, you need to divide it by 7. Denominator 7. Okay, after simplification, it's 17 over 7. That's the exact answer. It's not approximate answer. It's not approximate answer. That's exact answer. Okay? Yeah. So for n relatively small, we need to calculate average number of comparisons in this way. For n is large, then we cannot do it. Yeah, it's hard to do it in this way, when n is very large. Yeah, so we will approximate average number of comparisons. We will do approximation for the number of comparisons. All right. Yeah. Yeah. All right. Yeah. All right. Yeah. So try to understand this example. Yeah. Yeah. Because I may give you a question. I may give you a question with a different number. Yeah. With a different number, can you still use the same way to find the answer? Right? Yeah. Okay. Yeah. All right. Then, so let me give you just for the general case, for large N, for large general N, then it's hard to use this way to calculate average case. So then we may need to consider approximation. For large N, most of the time we need to use the approximation formula. So here, I just talk about that approximation. Formula. Okay, all right. Yeah. All right. So approximation here, I want to compare worst case and average case. Okay. Yeah. The worst case. We know the worst case, there are 2 formulas. Or okay. Yeah. The average case, it's hard to write a general formula. It's hard. Okay. Yeah. Average case. Yeah. But here I can give you an idea the difference between the average case. So the worst case minus average case, the difference is less than 1. So you can see the average case is very close to worst case. The difference less than 1. Less than 1 comparison. Think about that. That means your worst case number is very good approximation to the average case. Think about that. For binary search, the difference is small, less than 1. Okay, Yeah. All right. Yeah. Yeah. So you get the idea. That means the average case, if you use some number like this, it's pretty good approximation, right? Yeah, pretty good approximation. Okay. Think about it. You use this expression for average case number of comparisons. It's a very good. It's not exact, but the difference is so small. Difference is very small, less than 1. Yeah. We should be very happy when n is relatively large. We should be very happy. Okay. Yeah. All right. All right. Yeah. All right. So we just have a few more minutes. Yeah. But for the general selection problem, yeah, because this topic, I want to go a little fast. I do not want to cover the details. Yeah. So here, I just want to give you some basic facts. Okay. Yeah. Actually, I remember I give you something before. Yeah. So the general selection problem. So first, the general selection problem, find the kth smallest element. That's the general selection problem. Okay. But we consider the median when k equals n over 2. So that's the median. So that's the median case. Yeah. For the median case, to find the median, there exists big theta of n algorithm. Okay. Yeah. Linear algorithm. People also call the linear algorithm. Yeah. That means we do not need to sort the whole array, because when we sort the array, we need a big theta of n log n. Okay, big theta of n log n. Okay, yeah. But this finding the median, it's a linear algorithm. So you can see it's faster. Yeah. But here I like to give you another example. Yeah. Here, yeah. Compare two questions here. Yeah. 2 questions. The first question, sort a 5-element array. Second, find the median of a 5-element array. All right. Both questions pretty hard. We want to find the best solution. So both questions are very hard. Yeah. So I won't assign you. Yeah. So if you want to try, you can try. The best solution for the first question, 7 comparisons. 7 comparisons. Yeah. If you look at it from our lower bound, remember we have a lower bound. Lower bound for the number of comparison, 5 factorial. Seeding function is also 7. 5 factorial, log of base 2. Seeding function also 7. That means we can reach that lower bound. We can get lower bound number of comparisons. That's the best. Okay. But find the median. This question, the answer is 6 comparisons. The best answer, 6 comparisons. Okay. Just one fewer than that sorting counterpart. Sorting counterpart. Only one better. Yeah. The best you can do, 6 comparisons to find the median. Yeah. So these 2 questions are very challenging. Okay. Yeah. Very challenging. When I have a chance, I may show you how to solve. Yeah. All right. All right. So let's stop right here.